Nab it. I went to 2 pages. Okay, let me recap. Okay, we're talking about inverse functions. Well, we test it by doing composite functions, f of g of x, which means that the g of x is inside f of x. Take the g function, put in place of x, and the f function, and work it out. Equals x. Same thing the other ways. F of g of f. So take the f function, put it in place of x, work it out. If they both equal x, that means they're inverses of each other. To find the inverse of a function, if you're given points, just switch the x and y's. And the inverse function is represented by -1. But if we give you a function, to find the inverse, first switch x and y, then solve for y. And this is what you get. And you just tested it. Okay. If a function has an inverse, then it is said to be 1 to 1. And I'm just going to write it 1:1. One to one means this. A function is 1 to 1 if any change in x produces a change in y. So if any change in x produces a change in y, then it's said 1 to 1. For every 1x, there's 1 y value. If we have 2 numbers and they're not equal, and we plug them into the functions, then they're not going to be equal. If the x's are not the same, then the y's cannot be the same. If the x's are equal, then the y's should be equal. That's what 1 to 1-ness means. And here's what happens. The domain of the function and the range of the function, of the original function, the domain is equal to the range of the inverse. Oh, sorry. So the domain of the original function equals the range of the inverse. And the range of the original function equals the domain of the inverse. What does that mean? Domain of the original function equals the range of the inverse. And the range of the original equals the range of the domain of the. Well, what does domain deal with? The x's. So the x of the original is the y of the inverse. And the y of the original is the x of the inverse. And that's exactly what we said we did. Remember what we did here? We switched X and Y's. So the domain of the first one is the range of the second. The range of the first is the domain of the second. So that's what it means in the long scheme of things. Now, to prove one-to-oneness, f of A has to equal f of B if A equals B. In other words, here's an example. This is how we test if something has one-to-one. In other words, if it's one-to-one, that means it also has an inverse. All right, so what this means is this. We're assuming that A equals B. So f of A has to equal f of B. Let's plug it in there. So we have this first one, we have 3A plus 2 equals 3B plus 2. So far, so good? Because according to the rule, it says if A equals B, then f of A equals f of B. Here's our function. Let's put A in front of here and then put B on that side. If we subtract 2 from both sides, what happens? 3A equals 3B. If we divide both sides by 3, what do we get? I was catching my breath. But what we do here is, what we're trying to do is once we switch f of A equals f of B, and we put the A and B in there, and if we can simplify it and we end up with A equals B, then it's a one-to-one equation. The only way that could be true is if A and B are equal. If A and B are equal, then what we have graphically we have the horizontal line test. Earlier, we talked about the vertical line test. Anybody remember what the vertical line test did?
It's where you draw a vertical line on the graph.
Okay, if it doesn't cross it more than once, what does it mean it is? It's a function, yes. A function. So now we're dealing with functions here. Very good. I'm glad you guys remembered that. If you draw a horizontal line across a graph, and it only, I'll say crosses one time, then the function is one-to-one, which means it has an inverse. So the horizontal line says this: if you draw a horizontal line and it only crosses the graph one time, then that tells you that the function is one-to-one, meaning that it's possible to find an inverse of it. Okay. Good there? Here we have 4 graphs. Is the first one a function?
Yes.
Yes, because I can draw a vertical line test. So it is a function. Is it a one-to-one function? No.
Because it will cross one out.
Yeah, if I do a horizontal line, so not one-to-one, meaning that there's no inverse to it. Is this one a function?
No, it's not a function.
Not a function. Is it one-to-one?
Yes.
Yes, but it is one-to-one, which means it does have an inverse. This one, one-to-one?
But it is a function.
But it is a function. Very good. Anybody remember the formula for this function?
To be something we haven't heard of since the 8th grade.
Absolute value. You've heard of that. That's the end of chapter 1. Oh, so. And this one is a function and one-to-one. That's a linear equation. Let me show you how the proof of a function that's not going to work with that, the test for one-to-oneness. Let's pretend our function is f of x equals x squared. Remember, we're testing one-to-oneness. This would be quadratic. This would be a parabola. Remember, there's f of a equal f of b. So a squared equals b squared. If I square root both sides, what happens? Remember what happens whenever I did this. If x squared equals 4 and I square root it, x becomes what? Whenever you square root a squared number, you have to take the plus or minus of a number. So since I square rooted that, it becomes plus or minus b. So is it one-to-one? No. A can equal b, or a can equal negative b. So that's why it's not one-to-one. So whenever you're asked to test if it's one-to-one, just take the function you're given. One side put a in place of x, one side put b, and work it out. See what happens. All right, that does it. First part of section 1. Chapter 5, section 2. Exponentials, functions. Okay, we thought we had exponentials before. That is not an exponential function. That's just a function with an exponent in it. An exponential function has the variable x as an exponent. So this is the way it looks. A to the power x, the base. This is your exponent. And this is your base. There are conditions here. A has to be greater than 0. And A cannot equal 1. If A equals 1, anything you set the power to is always going to equal what? 1 to any power is always going to be 1. So that's just a boring straight line. Now, we can't use negative A, because think of it this way. If A was negative, and the x changes, what happens to the numbers? What is negative 2 squared? Positive 4. Negative 2 times negative 2. If I had negative 2 to the third power, negative 2 times negative 2 times negative 2 is negative 8. Negative 2 to the fourth, negative, 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 negative makes a positive 16. So you see how it changes signs each time. That's the reason A has to be positive. A cannot be negative. We cover that in calculus. It's called an oscillatory function. It oscillates up and down. It's like a porpoise. So here are the properties of our exponential function. Because it has a function to it, it has to have properties. First property, like we said, A has to be positive and A cannot equal 1. It has to be continuous. What does that mean? If I say it has to be continuous, what does that mean? Well, if you start at one end of it with your pen, you could draw the rest of the graph without ever lifting your pen. It has to be continuous. It cannot have any breaks to it. Since it's continuous, has to be 1 to 1, meaning we can't draw a horizontal line across it more than once. The domain of the function is all real numbers, from negative infinity to positive infinity. That's what R means. The range is from 0 to infinity. So we can use any x's we want to, positive, negatives, and zeros, but the final answers will always be positive. No, it won't be, because it doesn't have an x-intercept. Number 6. It's an increasing function if A is positive. I should say positive. We know it's positive, has to be bigger than 1. If A is bigger than 1, an integer, then we know it's an increasing function. It's a decreasing function if A is between 0 and 1. And I'll show you what this means in a second. The horizontal asymptote equals 0. The x-axis. That's why I told you, that's why I said the range has to be above 0. It can never cross the x-axis. So the horizontal axis, you never touch it, cross it. And then the y-intercept is always at 0, 1. So these are the properties of exponential functions. Let's look what that means. I'm going to look at both of these actually. That'll prove the rest of these. I'm going to say a equals 2 and a equals 1/2. We could plot some points here. Remember, the domain is all real numbers. I could pick negative numbers. I could put 0, and I could put positive numbers in there. So if x is -2, I have 2 to the power -2. What does that -2 power mean? It's on the bottom. So 1/4 is my first point. When x is -1, that means 1/2 to the first, which is 1/2. Two to the 0. Anything to the 0 power is what? 1.
I'm thinking multiplication.
Well, this,
Kind of.
but exactly, but there's nothing to multiply yet. It's 0 power. So 2 to the first power is just 2. And 2 to the second power is 4. 2 times 2 is 4. So the graph of this one so the bigger the negative number, the smaller the y. So it starts out here. It crosses at 1. And it goes up. It's an increasing function. So like I said earlier, if it's increasing. If the base is bigger than 1, that means it's an increasing function. Let's look at what at 1/2. We use the same numbers because the domain's the same. So if x is -2, you have 1/2 to the power -2. The negative exponent means flip the fraction and square it. So 2 squared is 4. One-half to the -1 power. Flip it. So it's 2/1 to the +1 makes it 2. 1/2 to the 0 power is 1. 1/2 to the first power is simply 1/2. 1/2 to the second power is 1/4. So at -2, it's 4. At -1, it's 2. At 0, it's 1. At 1, it's 1/2. At 2, it's 1/4. So it's a decreasing function like this. Like the property said. If a is greater than 1, it's an increasing function. If a is between 0 and 1, it's decreasing. So far, so good. It's boring.
You're not funny with my first one.
Yeah. Oh, my boat. Okay, now let's look at some transformations. Yeah, I'll take my time. So what kind of transformation you think, what kind of shift is this? Is it horizontal or vertical?
How would you tell?
Look at the change. Well, first off, you look at the original function is 2 to the power x, right? What does that graph look like?
So.
But now,
-2 degrees, right?
no, because in other words, it's a horizontal shift because I have to change the value of x first before I do the function. So what this one says, if I set this equal to 0, what's happening here is I shift it 2 spaces to the right.
Oh.
There's my new graph. So it's going to cross through there. It still has the intercept of 1, but I shifted it 2 spaces to the right. Think back of chapter 2. Whenever we talk about anything that affects the x first is a horizontal shift. As opposed to this. Does it affect the x or does it affect the y? So this is a vertical shift. So the original graph is 2x. But I now have to shift it down 4 spaces. From my origin, I move it down 4 spaces. 1, 2, 3, 4. There's my new origin. And my graph will look the same. It's still going to cross through there. The cross is at -3. But if you think about it, if my original y-intercept is 1 and I subtract 4, I get -3. That's my new y-intercept. The origin used to be here at 0, 0. It's now at -4. How about if I gave you this? What's that graph going to look like? Does it have a horizontal shift? Is there a change in x? No. There's no plus or minus to x. Yeah, but now what is 1/2? Is that, does that mean it's going to be increasing or decreasing function? Well, remember, this base, the base has to be positive. We have 2 other conditions. If a is greater than 1, it's an increasing function. If A is between 0 and 1, it's a decreasing function. It's a decreasing function. Because 0.5 is the same as 1/2. So it's a decreasing function. What happens if I change the sign in front of it? So where does it flip? X or Y? Are you sure? Yes. Good. Because all I do there is I take all my answers and now make them negative. I take all my answers that are positive and now make them negative. Okay, what if I change the sign of X? What if I change the sign of X? Because the original function looks like this. So if if I have a negative number, it's a big number. But if I take a negative of negative, it's on this side. So what this graph looks like is I flip it across the x-axis or the y-axis. Because now I changed all my x's. Instead of putting -2, I put a +2 in there. So it just flips it across the y-axis. Look for some more examples here. The most common applications for exponential terms is with business. Business and science. If you ever take a business course or an accounting course, you'll see this formula a lot. Actually, if you're going to buy anything, you're going to see this formula a lot. This is called the compound interest formula. Compound interest just means that what is interest in it's a penalty if to pay back extra than what you borrowed, right? That's interest. But what banks do, and then now they're raising them above 19%. It's outrageous. Yeah, so you get a credit rating, you have to get a credit history.
That's why I earned the interest. But if you do like a credit card, it's best to get like a gas card and pay it off monthly so that you don't have like a
Don't carry a balance, right? You see, that's good, but you should extend it.
Yeah.
Because the longer you pay off on it, and it shows that you can pay it off. If you do it one time, there's no history. It's just one shot, one snap deal. So
I still have, because I pay mine off in $500 like
Installments.
increments. I still have $10,797 to pay off. So I'll still pay off for several years.
yeah, so $500 a month. Every 2 months you pay 1,000. So you need to make it. So you need 22 months. Basically, you're looking at exactly 22 years, exactly 24 months to pay it off, including interest. Anyway, but this, what they have here is the compound interest. The letter A stands for what's called an annuity. Annuity is the total amount of money that you'll pay back at the end of how long you borrowed money. Total amount due or paid. P is called the principal. That's the amount borrowed. R is the rate. It's the percent in decimal. In other words, if you borrowed at 20%, that becomes 0.20. Yeah. Or 15%, 0.15. Just drop the percent, move it two to the left, and you're done. Yeah, a lot of people don't see that. T is the time of the loan. This is in years. And N is the number of times the amount is calculated. In other words, we're saying, example, if I say annually, that means N is 1. If you pay annually, it's only done one time. If I say semi-annually, that means I do it 2 times. If I do it monthly, what is N? How many months are there in a year? Right, 12. If I do it weekly, where? Just example, EX, examples. If I say weekly, then N is 52. Daily, N is 364. Either 64 or 65, depending on which system they use, because businesses are all closed on Christmas. So we can't do business there. So 64. If I say quarterly, what is my N? How many quarters are there in a year? 4. Yeah. There are 4 quarters. So that's the only part yet you have to listen to and read when you're looking at the stuff. And once you have all those, you plug in your calculator and you're done. That's it. But definitely see this, and this kind of stuff you need a calculator because of the structure of the formula. Now, that was used by businesses for the interest. The same formula is used in engineering and sciences. All right, so we'll look at the same formula, but a gentleman by the name of Euler, a mathematician, he started off with this same formula. And he said, what if we borrowed $1 for a rate of 100% for 1 year? We had 1 plus 1 over n times 1. So what this becomes? So it's just 1 plus 1 over n to the power n. As n goes to infinity, this number approached a number 2.718128, blah, 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 which he now changed to e. Because it's a constant term. And very soon, you'll see where this is going to be used. Okay, so that's the introductory part of exponentials. So he took this formula as n got bigger and bigger and bigger, it approached a specific number. And that number we call E. Okay, that does it for section 2. Now let's look at section 3. Logarithmic functions. There's a reason we started off this chapter by talking about inverses. Because exponentials and logarithmics are inverses of each other. Logarithmic functions are inverses of exponential functions. So here we have our original function, the 2x. We know it looks like this. That's this one. How do we find the inverse of this? We switch x and y. What that one becomes is this one. It crosses at 1. This one crosses at 1. Inverse functions are simply flips across the line y equals x. If we drew this one and folded it over the line y equals x, we get the logarithmic function. This one is y equals log base 2 of x. And that's what we're going to learn today on this section, how to convert all these things. So instead of writing logarithmic equations from now on, we're simply going to write the word log. And there are 3 different types of logs, which we'll talk about in a second. So log, this is read log base a of x. is the inverse of f of x a to the power x. Let's look at their properties. So the exponential function, the properties there this is the way they look. Two. The function is a to the x. The inverse function is logarithm a to the x. They have to be continuous. They have to be one-to-one. Remember, in order for the inverse to exist, it has to be one-to-one. The domain of exponential functions is negative infinity to positive infinity. The range is all the positive y's. Has to be greater than 0. Yeah. That's the exponential function. Now the logarithms, remember, they're inverses. So the domain of the inverse is the same as the range of the regular function. So these two have to be equal. That means the range of the inverse is from negative infinity to positive infinity. They're both increasing functions. Dang, I wish I had more space. They're both increasing functions. The horizontal asymptote of an exponential function is the x-axis. You need more paper?
No.
The vertical asymptote of the logarithmic function is the y-axis. So it has no, the exponential function has no x-intercept. And the y-intercept is always at 1. The x-intercept of the logarithmic function is at 1. And it has no y-intercept. As you can see, because the domain is the range, range is the domain, no X, no Y, X1. So they're inverses of each other. They're mirror images of each other. Let's go ahead and find some logarithmic functions. All right. So the first one, the log 10 of 10,000. I'm going to jump straight and show you how to do this shortcut way. So if I give you this, basically what this question is asking, what power should the base be raised to equal this number? So it equals some number. We don't know what number it equals. No, this is log base 10 of 10,000. That's how the equation is read. So the way you convert this, take the base, push up the answer. So we have 10 to the y. Since the base is gone, the log disappears. So it equals 10,000. So what we have to do, 10,000 is 10 to the what power? 10 times 10 times 10 times 10. So it's 10 to the fourth power. 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. Since the bases are the same, the answer is 4. So the answer to this equation, this question, is 4. Let's look at that one. Remember what you have to do? Set it equal to something. It could be any, I'll say set equal to X if you want to, it doesn't matter. It has to equal something. We don't know what that something is yet. So we take the base, push up the answer. The log drops off, so it equals just 0.01. Since it's a small number, this is the same as 1 over 10 to the second. Because we move the decimal 2 to the right. We can rewrite this. Since it's on the bottom, we can bring it on top and change the exponent. Since the bases are the same, we know the answer is -2. So the answer to our question is -2. Let's look at another one. Let me show you what's happening here. Here's the conversion that we're going to be doing from here on out. Log base A of X equals Y. The base comes over here, so it's A to the Y equals X. So the A from the base is still the base to that exponent. We're using this conversion. How about this one? Log base 8 of A. Again, we don't know what it equals, so we just set it equal to something, X. Take the base, push it up, and the log drops off. Yeah, this is a 1, so X has to equal 1. That's your answer. Log base 2 of 8. Equals X. Take the base. So 2 to the X equals 8. What is 8 made up of? So it's the same thing as 2 to the third. 2 times 2 times 2. Since the bases are the same, the answer has to be 3. That's your answer. Log base 9 of 3. So we have 9 to the X equals 3. Right, so 9, the same thing as 3 squared. So we have 3 to the power 2x equals 3 to the first. The bases are the same. So what's x going to equal? So x is equal to 1/2. So the answer is 1/2. Oh, everybody finished? Or okay. Anytime, I mean, I'm looking to see how far we can get. I'm gonna try to get to one more section because we only have 7 sections in this chapter. I think. Or 5 or 6. But no, we'll finish definitely for sure on Wednesday. And then next Monday, if you guys want to, we'll take a vote on Wednesday. I mean, I could be here on Wednesday, on Monday for me too. I'm here for you all. It's Thanksgiving week, right? Log base 6 of 1. Work it out.
So you would do 6x equal to 1. And then you would.
Nope. Anything to the power of what makes it equal 1?
Right. That's over.
Which there are a couple of them that brought up a couple of properties. If you have a log base anything of 1, it always equals 0. If there's a 1 there, it always equals 0. And if the base and the number are the same, it equals 1. These are always true, no matter what. If there's a 1 there, then it equals 0. If these two are the same, it equals 1. Okay, so get the other direction now. Here's our conversion rule. Because now I'm going to give you this. 16 equals 2x. Write that as a logarithmic equation. Well, first solve it, and then write it as a logarithmic equation. I want you to do things here. So we have to try to get the same bases. So 16 is made up of 8 times 2. 8 is made up of, and 4 is made up of. So 1, 2, 3, 4. 16 is the same thing as 2 to the 4th power. So that means x has to equal 4.
Oh, that wasn't fun.
Now write this as a logarithmic equation.
So would you do log, and then I think you get 4.
What's the base?
Well,
Well, look at the conversion. We have this right here. This is your x. This is your a, and this is your y. Plug them in there. Of 16 equals x. All it is match them up. B 10 to the negative 3 equals that. Write it as a logarithmic. There's no x in there. It'd be log base what? Yeah, because the base has to stay the base. And these two change. How would you write that one?
Wouldn't you log e to yeah, e equals 70, or no, yeah, that's what I mean.
Because they remember whatever your answer is here becomes your exponent, or conversely. So whatever your exponent is becomes your answer. These two have to switch places.
So that's the answer, that's the answer.
That's as far as we can go. Let's see what else. Write that as an exponential. Write that as an exponent. So it's a, since it's logarithmic, so we have to a to the 8th equals what? Q. Log base 2 of 32 equals 5. So it's going to be what? 2 to the 5th. It's the base, pushes up the answer, equals 32. If it's a base here on the log, it has to be the base in the answer. All right, as there are three types of logs, depending on their bases. If we have a base 10, you need to borrow that? Let's see.
Are we meeting?
Wednesday, yes.
Okay, perfect.
See you then. Okay, so if we have a base 10, we call that a common log. Why is it called a common log? Because our numeric system is base what? How many figures we got? We have a base and we have a decimal system, tens, 0 through 9, 10 to 19, 23. So whenever we have a base 10, you don't have to write. If you have a base 10, you don't have to put it down there. Because it's common, that's standard. So if you see an equation, like we were doing, how would you put that into exponential terms? What's the base? It's base 10. So this base pushes that one up. So we have 10 to the y equals x. So if there's nothing there, it's automatically a 10. Those are called common logs. The next one we have is what's used in engineering, base E. We just talked about what E was. These are called natural logs. So whenever you have a log base E, we simply write ln of x. Stands for natural log. Logarithmicus naturalis, natural log. So if I gave you this and asked you to put it in exponential terms, what would it be? So this is log base E. So it's E pushes up, so it's E to the y equals x. And the last one is anything else. Anything else has to be written there. Anything else, just write that. So if it's not a 10 or an E, we just do it like we've been doing. Work those two out for me. What's the first one gonna equal? So if there's a 1 there, it's automatically equals 0. And if the base and this number are the same, it equals 1. Because this one is, which what say? This right here says the natural log of E equals 1. Oh, ln. LNE, yeah. Yeah, you'll always see it written in cursive. So it's, yeah, it's just 2 words. It's natural log of E. So natural log of X. That's true. I should make it clear. Yeah, it's not LNE is 1 word, like loan or something. It's the natural log of E equals 1, which is log base E of E. Okay, so far so good. The problem with your calculators, only compute base 10 or base E. Nothing else. So how would we solve? How would I solve for that number? We use the change of base formula. If your base is anything other than a 10 or an E, you have to use the change of base formula. The change of base formula is this. So we have log base A of X. Or we can use the ln. Whatever's here goes on top. Whatever the base is goes on the bottom. And we use logs. We use that ratio. The log of X over log of A. It's going to give us the same answer if we use natural log of X over natural log of A. So it doesn't matter which one you use, ln or log. So we use log base 10 of 5, log base 10 of 2. Or we can have ln of 5 over ln of 2. That will give you the decimal answer for that question. So far, so good? All right, let's move on. That's the end of section 3. So I want to get to at least the properties of these things. Now we're going to come look at the properties of logarithms. Yes, I'm really hoping you guys during the Thanksgiving break, which I hate to ask you to do it, but again, if you want me to, I'll be here on Monday. But I need you guys to start kicking up the pace and making sure you do all the homeworks and all the tests. Because I would like to spend that last week of classes before the finals just answering questions and going and ironing out all the ones you have trouble with. Definitely bring your laptops so we can do some answers here too. Okay, so my time is going to be yours, so make sure you use it well. Chapter 5, section 4. properties of logs. First one is a product property. For ease of writing, I'm going to make everything just log. I'll make a log base 10. So, but it works on all logs. If I have a log and I have a product of two numbers or two things, I can expand that by taking the log of each one separately and adding them together. So that's the product. If I'm multiplying them, I can split them up. Conversely, if I have the log same bases and I have two things, I can combine them and make them multiplication. In other words, if I had log of x plus log, let's make it log base 3 of 2, I can combine these as log base 3 of 2x. It means I can go both directions. The quotient property. If I'm taking the log of a quotient of a fraction, I can split them up by subtracting them. Whatever's on top minus whatever's on the bottom. And the power property. I take a log of a number to an exponent. That exponent goes out in front. And there you have it. So far, so good. These are the three basic rules that we'll use all throughout logarithms. Let me show you some common mistakes people make. What's the mistake there? If I'm multiplying the numbers inside there, I don't multiply their logs together. Only add them. I can't, if I have a plus or minus inside there, I can't add this to logarithms. That only works if I have a multiplication, then I can split them up. So if it's a plus or minus, you can't do anything with it. You're stuck with it. If I have a quotient, I can't take the log over log. Conversely, if I have log m over log n, I can't rewrite it as this. And if there's a exponent outside the logarithmic functions, I can't make it a coefficient. I can only do that is if it's a log of a number that's exponentiated. That's the only time I can bring it up, not if it's outside the parentheses. That means what I have to do here, I have to do this first and raise it to that power. Those are the properties. Let's look at some examples now. Log base 3 of 9 times 27. Since these are multiplied, what can I do? So what is log base 3 of 9? Work it out. Log base 3 of 9 equals some number. 3x equals 9. 9 is the same thing as 3 squared. So x equals 2. Do the same thing with this one. Log base 3 of 27 equals x. 3 to the x equals 27. 27 is 3 times 3 times 3. So x equals 3. You have to take these numbers and break them down. 27 is made up of 9 times 3. 9 is 3 times 3. So 27 is 3 times 3 times 3. So the answer is 5. This is how we use the mechanics, the tools of it, to solve our answers. Log base 2 of p to the third plus log base 2 of q equals what? What rule do we have? We have the same logs and they're added. What can I condense it? Where's just that? That means when you're adding them, I just take these two and multiply them together. Because you have to look at those properties and you have to be able to go both directions. What property can you use here? What property can I use there? The power, the product, or quotient? There's only 3 properties, ladies and gentlemen. Is it a quotient? Is there a fraction there? It's an exponent. Can you have an exponent? No, that exponent comes out in front. So -2 log base A of 11. That's how you write it. How about ln x to the 6? Because the exponent goes in front. And there's your rewritten part. Okay, now we're gonna go back to the earlier days in the semester. Hey, stay warm. First off, we have to rewrite this. What is 7, the fourth root of 7? How can we rewrite that? This is the conversion for logarithm or exponentials. If you have a square root, whatever this root is here, that's your denominator. Whatever you have inside there, the exponent, that's your numerator. So this number, what's this exponent of 7? 1 over 4. So that we got rid of that. So now, since we have an exponent, that goes out in front. There you go. It's these kind of small rules that we have to pick up on and follow along. There's only 3 of them, yes, but there's a lot of combinations of them. Okay, let's look at some bigger ones. All right, let's see who gets this one right. Let me see which one I want to use. Log x squared y to the 5th z to the 4th. Expand that for me. It's not that bad. Okay, the first thing you see is what kind of equation is it? What do you see here first? It's a quotient. So how do we fix a quotient? Take the top number minus the bottom number. That's the first thing we see. Okay, now we see a product. So the product means I add. Now we have powers. Those powers go in front. So we have 2 log x, 5 log y, 4 log z. And there you have it. Don't worry, I got plenty more for you. Okay, expand that one. Okay, we have a quotient, right? So the top is that minus the bottom. Now we have two products. X here's the minus sign. So these have to be in parentheses because now I'm going to change, because it's going to change their signs. Bottom line, this is basically what it's going to look like. If it's on the bottom of a fraction, it's going to have a minus in front of it. If it's on top, it's going to have a plus in front of it. So that should be a shortcut for later on. Since I know this is a product, I'm going to have ln m5 with a minus sign, minus ln n to the fourth. Now I have exponents. I can't have exponents, so they all come out in front. So they just come out in front. And there you have it. How about that one? There's a problem with that square root, isn't it? How do we get rid of that square root? Make it into an exponent. Remember the rule I showed you just a little bit ago? So it's xm over n. This is your denominator, that's your denominator. This is your equation, its exponent is 1. So we convert it there. So now, here we have ln of this whole thing. So this, before we do anything, this exponent has to go in front. So now I have ln of x squared y z to the fifth. So I took care of that. Now I got to do the ln of these. So I have ln x squared plus ln y minus ln z to the fifth. If it's on top, it has a plus, it has a bottom, it has a minus sign in front of it. These coefficients just go right in front of the ln's. So it's 2 ln x plus ln y minus 5 ln z. The last step, multiply 1/3 or divide each of these by 3. And there's your answer. 2/3 ln x plus 1/3 ln y minus 5/3 ln z. Let's go backwards. I'll give you the answer. You tell me the question it came from. In other words, I'll give you something like this. You give me this. Let's try that. Okay. 5 log base a of x minus log base a of y plus 1/4 log base a of z. Okay, so we have coefficients. What do you do with coefficients? Where do they come from? The exponents, right? So these coefficients become exponents. So we have log base a of x to the 5th minus log base a of y plus log base a of z to the power 1/4. We have a fractional exponent. What does z to the power 1/4 mean? Yeah, it becomes the 4th root of z. So this becomes log base a of x to the 5th minus log base a of y plus log base a of the 4th root of z. They're all log base a, right? If it's positive, if the coefficient is positive, it goes on top. If it's negative, it goes on the bottom. So this one goes on top. This one's minus, so this one goes on the bottom. Positive, so it goes on top. And there you have it. That's where it came from. Difficult? It's not difficult, it's just there's a lot of moving parts here. And you have to have your sheet next to you with all the formulas. Because the formulas go both directions. Okay. Convert that one into a single term. Okay, so let's look at these step by step. They have coefficients, right? Let's look at the numbers first. Leave the signs where they are, because the signs tell us whether it's top and bottom. And I'll show you how that works in a second. Well, let me do it that way. So here's a -2 here, right? So if we put that as an exponent, it's a -2 there on top of the x. This is a -3. But we can't, we need to have a sign between there, so it's ln y to the third plus ln z to the fourth minus ln m. So we got rid of all the coefficients. They're all ln's. So we have x to the power -2. This one's minus, so this one goes on the bottom. This one's plus, so this one goes on top. This one's minus, so that one goes on the bottom. But we're not done, because we have a negative exponent. Negative exponents go on the bottom. We switch their locations. So there's your answer. All of your answers have to have positive exponents. Like I said earlier, if it has a negative in front of it, it goes on the bottom. So this ln x squared goes on the bottom. This ln y cubed goes on the bottom. Ln m goes on the bottom. Well, I have one that you have to work out. Yes. Please make sure I'm not paused again, because that burned me up. Okay. Simplify this as far as it can go. The quotient, because there's a minus sign there. And they're both ln's. So it's going to be, this one's on top since it's positive. This one's on the bottom. Now what do we do? Factor the bottom. Because it's a quadratic. We factor it. So let's see what this looks like. Remember how we do this? If the leading term is not 1, we put 3x here, 3x here. The signs, that's the seconds of minus, what does that tell me? The signs are different. And the bigger number will be a negative. If the second sign's a minus, signs are opposite. And the bigger number gets the first sign. Okay, so first we put 3x, then the signs. Now we take the first and last term. 3 times 2 equals 6. So what times what equals 6? When we subtract them, we end up with 5. When we subtract them, we get 5. 6 times 1, 6 minus 1. Very good. So since this is a minus, the 6 goes here, the 1 goes there. Now in this one, can anything factor out? Yeah, we take out a 3, which leaves us with x minus 2. So the factors are 3x plus 1 and x minus 2. These cancel. So I have ln 1 over x minus 2. There's my final answer. I'm not gonna lie, it's gonna take practice. It will take practice. And again, don't hesitate to send me messages, ask me questions if we get stuck. Here, you'll also be faced with these type of problems. Let log of 2 equal 5. And log of 3 equals 2. This is I'm just saying, well, this is just for scenarios. A. What is log of 6? We can only use these things. How do we make up 6 with these two numbers? Isn't 2 times 3 same as 6? Since we have a product, I can split them up. Log of 2 is 5. Log of 3 is 2. So the answer is 7. So I take what I have, put it into what I need, and then solve it out. How about that one? Log 2 over 3. So what properties do we have here? We only have 3 properties. Quotient. Log 2 minus log 3. Log 2 is 5 minus log 3 is 2. 5 minus 2 is 3. Log of 81. What is 81 made up of? 9 times 9? What's 9 made up of? So 81 is the same thing as 3 to the 4th, right? So this equation I can write as log 3 to the 4th. 3 to the 4th is 81. Exponent says that comes out in front. What is log of 3? 2. That's log of 3 is 2. So the answer is 4 times 2 is 8. Let's try some more. Here we have log of 2 is 5. Log of 3 is 2. So the next one, log of 1/4. So what are we going to do with this? log 1 minus log of 4. 4 is made up of what? 2 times 2, which is 2 squared. What is log of 1? Ah, very good. And this exponent comes out in front, so it's minus 2 log of 2. What is log of 2? So the answer is negative 10. How about log of 5? So what is 5 made up of? Hmm? 1 and 5? Yeah, but we don't have anything here, do we? So that's the answer as far as you can go. What the trick was, C was going to do this. But you can't do that. You can't have a plus or minus aside there. So you can't go any further. Log of 3 over log of 2. What's log of 3? What's log of 2? That's the answer. That's all there is to it. Let me see what else I want to talk about. Oh, we haven't talked about solving them. So far, we've just done pretty rudimentary answers and questions. Solving equations. For example, if we had 2 to the power 3x minus 7 equals 32. Solve for x. What you have to do first, if possible, get same bases. So what is 32 made up of? 8 and 4. 4 times 2, 2 times 2. So 32 is the same thing as 1, 2, 3, 4, 5, 2 to the 5th power. This is called the base exponent property. If the bases are the same, the only way they can be equal is if the exponents are the same. Since the bases are both 2, the exponents have to be the same. Add 7 to both sides. 3x equals 12. Divided by 3. So x is equal to 4. That's the answer. Make sense? So if you have two numbers, first thing you want to do is try to get the same bases. If you get the same bases, set the exponents and you're done. Two to the 5x equals 64. Again, now 64 is made up of what? 8 times 6, right? Or 8 times 8. Yeah. 8 times 8. This is 4 times 2. 2 times 4. 2, 2. So 1, 2, 3, 4, 5, 6. So it's 2 to the 6th power. Since the bases are the same, that means the exponents have to be the same. The answer is x equals 6 over 5. So if possible, then the first thing you would do is get the basis to be the same. If that's not possible, well, let's do a couple more. How about this? 9, 3x plus 2 equals 27x plus 5. What's 9 made up of? 3 times 3, right? So it's 3 squared. What's 27 made up of? Yeah, 9 times 3 times 3 times 3. So it's 3 cubed. Remember, all of these rules we talked about in the past are not coming into play. What do we do when we have a power to a power? We have power to a power. You multiply them. Power to a power, you multiply. So here we multiply 2 times 3x plus 2. So we have 6x plus 4. And 3 times that, so it's 3x plus 15. We multiply those out. Now we have a common base. So we set the exponents equal to each other and solve for x. Subtract 3x from both sides. X equals 3x plus 4 equals 15. Subtract 4. 3x equals 11. X equals 11 over 3. But that won't always happen. Case in point. 3 to the power x equals 20. This will be the last thing we talk about today. Because it's already 3 o'clock. Let me get you guys on the road before it rains again. We can't get the same basis because 20 is not a base 3 number. We'll use what's called the property of logarithmic equality. The property of logarithmic equality says this. If I have 2 numbers, the same log, same bases, the only way they can be equal is if the operations are the same. So if that's true, then this has to be true. So In other words, here, we have to get rid of the x on top. Since it's an exponent, we have to take the log base 3 of both sides. Whatever you do to one side, you have to do to the other side. I set them both equal to each other. Why did I do that? Because now I have an exponent. This thing comes out in front. Log base 3 of 3 is what? Log base 3 of 3 is 1. What power does 3 have to be raised to equal 3? 1. So the answer to this equation is that. One more, then we'll call it a day. The earlier example, the last example, I used log base 3 because that's where my x was. It was a base 3. I can't do that here because I have two different bases. So what I have to do here, I'm just going to use a arbitrary one. I'm going to use ln. These exponents come out in front. So it's x plus 3 ln 4 equals negative x ln 3. I have a parenthesis, so I have to get rid of the parenthesis. I have x ln 4 plus 3 ln 4 equals negative x ln 3. Let's get all the x's to one side, all the non-x's to the other side. So if we subtract 3 ln 4 from both sides, I have x ln 4 negative x ln 3 minus 3 ln 4. Everybody follow what I'm doing so far? Kind of. Now I need to get this x to the other side. How do I do that? I have to get, so I want all the x's to one side. So I have to move this x. How? I add it. I have x ln 4 plus x ln 3 equals negative 3 ln 4. Remember, we're solving for x. So what can I do next? Look on the left side. Can we factor anything out? Do they have anything in common? The x. So we factor out the x. Now to get the X by itself, what do? I gotta get rid of all this stuff. So since it's multiplied, I divide. But look on the bottom, can I combine these two? 4 times 3, so it's ln 12 on the bottom. Yes, I do understand. There's a lot of steps, a lot of moving around, a lot of magic going on. We'll pick up from here next time. Yeah, we got next we'll start with doing these solving ones. And then that should pretty much do it for that chapter. And then we start chapter 6. All right, everybody. I know your brain's full of mush now.